Hello, today I'm going to show you how to solve the problem focus on trusses, and the questions in most of these kind of problem is to find the tension or the compression in all links of a structure like this when we have some external forces applied on some points, and we have some connection points like a pin here, another roller pin here, and the question here is that uh, how we can find the internal forces in each one of these members, and what is the best approach to do that. Actually, we have two approaches for solving the trusses and finding the internal forces. The first approach is going joint by joints, and the other one is using the cuts, and meaning that we are making some cuts, and using that cuts we can find the forces in the desired members. Let's start with the first approach, which is named joint by joint. And for doing that, the first step is that finding the forces which are applied by the joints, meaning that reaction forces which are applied on the structure. If we look at this system, what we have is a pin over here and a roller pin over here. We know from the previous sessions that the roller has only one reaction force, name it AY, and a pin which is fixed to the ground is applying two reaction forces, and we can name them CX and CY. Right now, if we do the free body diagram of this structure, you can see that actually this should be like this. You can see that what we have here is a Y, CX, and CY, where we are applying 400 newtons here and 600 newtons over here. And if you look at this structure, this is a freeway diagram of the whole system, and by doing that you can say me that I have three unknowns over here, and we know for any static problem in the plane or 2D, we can write down three equations, including sigma of x equal to 0, sigma of y equal to 0, and sigma m around any point equal to 0. Meaning that I have a x, a y, and actually cy and cx as the unknowns, and I have three unknowns and three equations, and I can solve this, and I can find the reaction forces. This is the first step that we need to do. After that, we need to go joint by joint, meaning that by finding the reaction forces, we can start from one joint and try to write down these equations for that joint, and going from that joint to the other joints. Okay, let's find the reaction forces here, and then we try to find the internal forces. I'm going to use these equations to find the unknowns. For doing that, at the beginning it's better to use sigma m, and for for the point I choose C because I have two unknowns over there, and if I take sigma m around point C, what I would have is Cx and Cy are not making any moment around that point because they don't have any R, and I have three forces including Ay, which are making some moments around point C, and I consider the counterclockwise direction as the positive direction for the sigma m. And for by writing down the sigma m around C, I would have a y with which is making a clockwise. If you look at this and you put your finger here, the type of rotation that this force is making is like clockwise motion, if you assume that it is going to make a motion around this point. That means that Ay is making a negative moment around point C, and its arm, if you consider this is the perpendicular arm of this force around that point, meaning that this should be times 6. 400 is making a counterclockwise moment around point C, meaning that that would be plus 400 times the arm of that is this length, which is equal to this. It's 3, and 600 is making counterclockwise. If you put your finger here, this guy is rotating counterclockwise around that. That would be plus 600 times 4 equal to 0, and if you simplify this, that would be 6 times Ay equal to 1200 plus 2400, and if you do this, that would be 6 Ay equal to 3600, and if you divide both sides by 6, you would get Ay equal to 600. And by having Ay, you can use the other formulas, including sigma fx and sigma fy. This one and this one gives you Cx and Cy. If you write down sigma fx, you can see that you would have, if I write it down here, Cx plus 600 is equal to 0, meaning that Cx is minus 600. And if you write down sigma fy here, that would be 600, which is Ay, minus 400, and plus Cy equal to 0, and this gives you Cy equal to minus 200, meaning that those forces should be in reverse directions. And if I do the free body diagram with the known forces, I would have such a diagram like this, and I would have 600 over here, which is Ay. I would have 400 over here, and Cx is another 600. I have 600 over here, and Cy is 200, and I put it like this. And this is my free body diagram with the known forces. Right now we know the reaction forces, and we can start cutting through the joints and see how we can solve the reaction forces. Okay, let's get started from here. I'm going to do the plot again. here I would have something like this, and just getting back to make sure that I'm doing the right thing, and I would have 600 over here, 600 over here. I have 3, 4, 400 over here, 600 over here, and 200 over there. And the name of joints are like A, B, C, and D. I have A, it's A, B, C, and D. And the lenses are 3, 3, and 4. Okay, let's assume this is a pin. Okay, this is a pin which is connected to a roller pin which is under that, and we already have applied the reaction force of that roller, which is 600 here. If you consider that pin, this is pin A, it is connected to two members. One of them is here, the other one is here, and I have 600 over here. The thing is that we can write down the static equilibrium equations for a pin, meaning that I can say sigma of x is working, sigma of y is working as well. How about sigma m? Here we have just one point. We can write down sigma m around that point, but this is not working here, meaning that one of the equations is useless. You may ask me why. Why is that? Now the thing is that here we have all the forces going through the point, meaning that if you take moment, all the forces are going through that point and making this thing zero. It's inherently zero, meaning that you have two equations. When we are using the joints approach, we have only two equations for each joint. This is one of the fundamental differences between this approach and the approach of using CODs. And this is very important that you know. You can consider the joints that you have two unknowns. For example, why I'm not starting from point B, why I'm starting from point A, or why I'm not starting from joint D. This is very essential. If you start from point D, you have 1, 2, 3 unknowns. You have one known force like 600 over here, but you have 3 unknowns. If you write down these equations for that point, you cannot solve it, because 1, 2, 3, 4 forces are going through this point and they are making zero moment. This formula is useless. This is very essential to know where we can start with. How about C? Yes, we can start with C as well. Why is that? Because we have 1, 2 unknowns. Then here is one important note, that we can start after this is the second step. After finding the reaction forces, we start with a joint which has two unknowns. We cannot solve more than that. Okay, then let's start with one of them, C or A. Okay, I start with A here, and I put two forces over here. There is one good point regarding the direction of these forces. It's not mandatory to put them in the correct direction, meaning that it's totally arbitrary to put them like, for example, going upward or downward or to the left or right here. But there is a good idea how to find them even when we don't have the values. Okay, I would say that if you consider this joint, this force is going to push this upward. This guy is not preventing that. This is a horizontal force over here, and let's put a line for that. And I'm putting another line for this guy. The question here, this should be upward or downward. This should be to the left or to the right. That's the question I'm trying to solve that. As I said, it's not mandatory at the beginning. You can find them without doing this, and if you get negative value for them, you change the direction. But there is a good way to find that. And I would say if you consider this as in a static equilibrium condition, this force is going to push up this joint. The only link which is preventing that is this guy. This guy cannot be upward. This force cannot be upward, because in that case this should this start moving upward, meaning that for preventing that motion, this guy should be downward. Right now I have two forces. I'm going to satisfy the static equilibrium conditions. I would say if you consider motion to the left and right, this guy is not dealing with that. This guy just push up this point. But this guy is pushing this guy to the left, meaning that this force should be in this direction, meaning that these two are fighting to keep this guy not moving in the horizontal direction. These two are fighting with each other to prevent motion of this guy in the vertical direction. And that's how you can find the correct direction of these two. And we put two unknowns for these guys, and at the end of the day you would see that the value of these guys would be positive, meaning that the direction of them have been chosen correctly. Okay, let's name them. I would say this is F, which is applied from B to A, and this is F, which is applied from D to A. And right now you can see if I use this one, that would be 0 equal to 0, because every forces are going through A and there is no arm for them. Then this guy is not working, this equation is not working, and I'm using only two equations for two unknowns. Sigma of x equal to 0 and sigma of y equal to 0 are those equations that are helping me to find my unknowns. Okay, let's write down sigma f y. And why is that? It's better to start with that, because if you write it down you can find it directly. But if you write down sigma of x, firstly you have two unknowns, and my suggestion is using sigma of y. And as I saw, as I showed you, that these two are fighting with each other in vertical direction, and firstly we found the direction of this one, meaning that it's better to start with sigma of y at the beginning, like finding the direction. Sigma of y is easier to work with. And if we consider this triangle over here, I have 4 over here, and I know this is 3, and let's name this guy theta, and sigma of y would be I have 600 positive going upward, and I have minus fba times sine of theta, and I know if I have a triangle like this, 3 4, this would be 5, and this is actually 0, and 600 is FBA times sine of theta, which is 4 over 5. And if I find this guy, that would be, if BA would be 5 over 4 times 600, which gives us 5 times 600 over 4, which would be 5 times 6 times 100 over 4. You can simplify this 25, and you can say that just give me a second to find the solution of this. That would be 5 times 6 times 25. That would be 715 newtons, and as you can see, this is a positive value for that. Right now I can do sigma of x, which is FBA negative times the cos of theta plus FTA equal to 0. And if you do this, that would be 750 times 3 over 5 plus FDA equal to 0, and FDA would be positive, give me a second to do this as well with my calculator, times 3 over 5, that would be 450 newtons. And this is FDA, and I have FBA equal to 750. As you can see, the magnitude of these forces are positive, meaning that the directions are selected correctly, and we don't need to change the directions of those. Okay, right now we are done with this joint, and we have found the forces which are applied by these links. And the first question is that what are these forces, and how are the forces of these links? Is it a tension or is it a compression? If you consider the links, for example, this is link AB. This is the force which is applied by this link to pin A. Again, this is the force which is applied by the link of AB to the pin of A. We know the reaction of that is applied on A. Okay, right now this guy is starting moving this way. For preventing that motion, you need to put a force like this at point B, meaning that AB is under compression. Then FBA is 750, and that will be compression. How about DA? If we do the free body diagram of that link, that would be AT, and you're seeing that this, what is this force? This force is what the link AD is applying on the pin A. These are two different things. Pin is different from the link. FDA is what is applied by the link AD on this pin. The reaction of that would be applied on the link, meaning that I would have force over here exactly with the same amount of value, but in reverse direction. For preventing the motion of this guy, you need to put a force over here. Okay, this is exactly FDA, but in reverse direction of this, meaning that my link AD is under tension. This is tension. Okay, then I put T over here, meaning that. Okay, when we are going to but by solving this, we already found the forces which are applied on link A, and we can go on joint A, and we can go to other joints and do the same things, meaning that by going to joint B, right now we can say we have two unknowns. Before that we had three unknowns. Right now we have two unknowns because one of them is found. We can go to joint D as well, because before that we had three unknowns. Right now one of them is found. The question here is how to put the force. We know the magnitude of that. This is FAB, which is applied on this point, but how is the direction of that? I would say that we need to do the same reasoning over here, because here we said that this is the force which is applied by this guy, and then we put the reverse of that on this point, and we said for keeping the static equilibrium conditions for the AB, we need to put this guy here. What is this? This is what the pin B is applying on this guy. Then the reverse of this guy will be applied on point B, meaning that if I do the free body diagram of point B, I know that the force is applied on this direction, on that. This is a known force, and the magnitude of that is 750. And the same story for D. I know this is the force which is applied by the pin on the link. The reverse of this guy with exactly the same magnitude is applied on D, and meaning that if I put point D over here, I would have 450 as one of the forces over here. I just want to complete the directions for these two, and try to find the correct directions for the forces, and then we can do the same approach for finding the magnitude of the forces. As you can see, we have 1, 2 unknowns here and 1, 2 unknowns here, and if I put the forces, one of them would be in this direction and the other ones in this direction. Here I want to do the reasoning to find the correct directions of these ones. As I said, it's not mandatory, but it's very helpful. If this guy is moving this guy to the right, this guy is the only one which is preventing that this should be this way, and right now this push up this point. The only one which is preventing that is this force. The same story here. This guy is pulling this point to the left. I need to put a force like this to prevent that. Right now this guy is pushing down this guy, then I put a force like this. These are the new unknowns. This is F, which is applied from C to B. This is the force which is applied from D to B, and I have F CA, and I have F BD, and these are two separated things, actually not related to each other. I just wanted to show you how to find the correct direction of these ones. Right now we can write down sigma of x and sigma of y for this one. The same story here. Another good approach for finding these two is writing down the sigma of x and y for this guy. That would be pretty easy because these ones are the only forces which are applied on this. This would be 600 and that would be 200. And by knowing these two, you have only one unknown over here. That was one of the example that is using the joints, and by learning that we can solve a lot of questions. The only thing that you need to know is how to start and which point you want to start. Before doing that, as I said in the previous session, finding the zero force member is essential. For example, here let's make the roadmap for solving this. I would say the zero step or first step is finding the zero force members, and then finding the reaction forces if possible. I would say sometimes it's not possible, sometimes we have four unknowns and it's not possible. I would say in some examples how to do those things, but let's assume that reaction forces by doing free body diagram of the whole system. This is step 1. Step 2, step 3, start with the joint, and I would say here that this guy is a zero force member, this guy is a zero force member, and this guy is not, and this guy is not, because we have some forces over here, and we can say this guy is not. And if I simplify that, I would have structure like this, and these are the forces which are applied on this guy. P1, C, this is P, I have P2. P1 and P2 are known. I put the unknowns with a different color. That would be AX and AY, and this is CY. And right now you can do the free body diagram of the whole system in step 2 and find AX and AY and CY, and you can start from here. And as you can see, you have two unknowns over here. By finding that, you can go step by step. If you find one of the unknowns, you can get here, and you would have 1, 2. If you get this one, these two are known, these two are unknown, you can go to E, and these ones could be solved independently. And yeah, this is the way that we can solve this. Another example, maybe here, the first step is finding the zero force members. I have one here, this is 0, and I don't have any other. Here is one example that you cannot do the free body diagram of the whole system because you get 4 unknowns. If you do that, you have CX, actually CY, and you get AX and AY over here, and you cannot doing that. But you don't need that because we can do the cuts from here. In the previous ones, we had a roller, for example, over here, and we could do the free body diagram of the whole system. This is one example that we cannot do the free body diagram of the whole system, meaning that you can go from this point. If you this is zero force member, we can get rid of that. This is one link, this is one link, and that if you solve this, you can get these two. You have 2 unknowns for here. This is done. You can do this and get here. You have these ones obtained from the previous sections. Find these things, these two, and the same story here. 2 knowns and 2 unknowns. You can get these things, and that's done. For these cases, you can see we have 2 pins fixed to the ground, and you have some forces or somewhere, and you can start with that point. Actually, you write down the equations for this one and start with that. In the next session, I will try to show you how use the cuts and what is the difference between this and that, and when we are using this and when we are using that. Thank you so much.